from it, of course, as we now know. But he goes on to say in this green box out here, he put forward a conjecture, which obviously turned out to be right as we now know it, but it was a conjecture at that time. This explanation is supported by the fact that the diminution in frequency of the same order of magnitude as the frequency of molecular infrared absorption lines, which is, as we know, due to vibrations in the infrared range. And it is found that the shift of the wavelength is not quite the same for different molecules, and this supports the explanation suggested. And this, of course, turned out to be the right thing, as we now know the connections between light interaction with vibrations and the Stokes and the anti-Stokes shift. While I'm going to talk about energy and climate, I did want to just mention, I couldn't let this opportunity go, some of the work that's going on in my own lab on light matter interactions. And the question we're asking is, can light matter interactions be observed and studied approaching atomic scales? We know that molecules and single atomic defects in materials absorb light. The question is, can we image them? Can we understand and study them at the atomic scale? But there's a big problem with that. The difficulty is the following, that if you plot the wavelength or the inverse of the momentum with energy, you find that photons, electrons, and neutrons follow in different lines, of course. And the most interesting part of the spectrum, or the energy spectrum, that is interesting from the chemistry point of view, is in this range of 1 milli-electron volt, which is where vibrations and phonons and all exist, on the order of 10 milli-electron volts or so, all the way to about 10 eV. And then you go into core electron states of matter, which are of course very interesting, but the chemistry by the valence electrons are in this range. The problem is that if you want to study optical behavior in this range, in this energy range, the wavelength of the photons are on the order of the infrared to maybe UV range. And if you try to image that, the diffraction limit is on the order of 100 to 200 nanometers or so, which obviously is 1,000 times more than the atomic scale. There have been, of course, development of super resolution techniques. There was a whole set of Nobel Prizes given in chemistry in 2013 on super resolution techniques. And that can get you up to about 5 nanometers at best, 5 to 10 nanometers, but it's still not the angstrom scale. And the question we're asking is, can we even beat this limit and go down even further? This, of course, has implications not just in physics of materials, physics in condensed matter, but in chemistry, biology, et cetera. And the problem is that it is very difficult to do that with photon because of its inherent wavelength. On the other hand, we could use electrons. We can focus electrons with lenses, magnetic lenses, and you can get to the atomic scale, except that the energy of the electrons is very high. The question we were asking now, and the approach we're taking is, can we mix the two? And just to sort of give you a very quick flavor, this is a paper that just came out last week on putting inside an scanning electron microscope. And in a scanning electron microscope, as many of you know, you have an electron beam that comes from the top, and that is on the order of 5 kiloelectron volts all the way to 30 kiloelectron volts or so. And the electron penetrates the material and then goes through a cascading scattering, inelastic scattering, and it produces secondary electrons. And you detect the secondary electrons, and that's your way of imaging materials down to about a nanometer or so, roughly a nanometer. Now they're pushing the limit even to sub-nanometer scales. What we are doing is to ask the question, if you shoot light in that, will the secondary electron production be modulated by absorption of light, because absorption of at least visible light also excite electrons, but across maybe in a semiconductor from the valence band to the conduction band. And would this be modulated in any way, the secondary electron? And the answer we found is indeed it can be modulated. We are now looking at spectroscopic imaging of this is silicon at 532 nanometers, 980 nanometers, it does not absorb. Silicon absorbs very little. Germaniums absorb both. We are down to about 10 nanometers or 10 or 12 nanometers in spatial resolution. We think we can get it down to nanometer or so. The physics, of course, is very interesting because, as I said, the primary electron enters the material, goes through a cascading reaction and inelastic scattering. And then the secondary electron comes out, and we are modulating the secondary electron. Most likely that we have found is due to photovoltage creation of the surface photovoltage that is created. And the question we're asking is, can we go down even further in terms of spatial resolution? But at the angstrom scale, the best microscope to use is probably not the scanning electron microscope, although it's easier with an SEM, but to use a transmission electron microscope. The TEM has gone through a major development with aberration corrections and others, and now we can see single atoms fairly easily. And we are asking the question: if you photoexcite matter in a TEM, can you see that with the transmission of the primary electron, which is anywhere from 80 kilovolts to about 300 kilovolts or so? And the idea is that for example, if you take a 2D material like boron nitride is a wide bandgap semiconductor, and the atomic scale defects of the missing boron or a nitrogen atom are optically active, are single photon emitters recently discovered. And they are so in the visible scale, and that is because you get gap states, and these gap states are optically active, and you can then and they become single photon emitters. The question is, how would a TEM be able to image the photoexcited state? And the idea is the following: that if you take an atomic scale defect, or a molecule for that matter, and if you photoexcite the material, your electrons are launched into a photoexcited orbital, which is a different shape than the ground state orbital. And if that orbital shape is different, it will change the potential distribution of the around that material, and that potential distribution will change the phase of the transmitted electron, and thereby you should be able to image that. And the question is, can we? We are still in that direction. It's kind of early right now, but at least our calculations on GW as well as DFT calculations, along with real noise measurements in these systems, suggest that perhaps we can get it down to angstrom scale imaging of the photoexcited state. Of course, this is a very difficult measurement because we are dealing with a single electron that is excited, and that is also has a lifetime large enough to be able to capture the orbital shape using the electron beam that is going through. I just wanted to put this, I didn't want to lose this occasion of talking or commemorating the Raman effect and light matter interaction. And I wanted to take this opportunity to at least mention what is going on in the lab in terms of the scientific work that we're doing. Let me now launch into energy and climate, the defining issue of the 21st century, which is the title of my talk. This is going to be less of the fundamental science that I just talked about, but more about issues that require science and engineering to really make breakthroughs that is really required to address this defining issue. Let me explain why I call it the defining issue. The first thing I want to talk about is population. This is the global population of the world. Today, we're at about 7.7 or 8 billion people, but you can see that this is a phenomenon only of the last few hundred years or so. Before that, the population, before the Industrial Revolution, was about 700 million people, and it has dramatically gone up due to availability of food, due to the green revolution of right before the Industrial Revolution. Food productivity went up because of crop rotation, as well as the Haber-Bosch process that created fertilizers, artificial fertilizers, in the early part of the 20th century, and of course Norman Borlaug's green revolution, that we are all a product of that. The global population is going to go up to about 11 billion people by 2100, about 10 billion by 2050. So another 3 billion people we're going to add to this world. Most of the population growth is going to be in Asia and most of it actually in Africa. During this time, an unusual thing happened, which is the per capita global GDP, not the GDP by itself, the per capita went up exponentially. And people became more prosperous. If that is a measure of prosperity, actually that's not the best measure, but nevertheless, it is used, the per capita GDP, and that went up exponentially. And the question is, why did this happen? What was life like? And we often sometimes forget what was life like. In some parts of the world, life is still like that. Life used to be like this. It's agricultural. The transportation used to be by horses, by animal power. And now we live in electrically lit and air-conditioned homes. We can watch Usain Bolt run the 200 meters. And on a television, we have healthcare. The life expectancy has gone up to about 70 to 80. We have world's information on our fingertips, and we can go locally in an automobile which has 100 horses in it, or fly across the continents in planes that have 100,000 horsepower in engines that we call jet engines. This transition is the Industrial Revolution, which is what I call horsepower to horsepower, because it was unthinkable about 150, 200 years ago to put 100 horses in a vehicle and take you to a grocery store. That was unthinkable at that time. Now we can do that right now. So the energy, and by the way, all of this had to do with energy. And if you look at any modern economy, the arteries and veins are the transmission of electricity, and the architecture that we follow today is still the Tesla Edison architecture of transmission system at high voltage, distribution system at medium voltage, and our homes at low voltage. That architecture is still the same. The devices, of course, are newer, but the architecture is still the same. And of course, on the oil side, we discovered oil from the ground in 1862 or so. And now we have, of course, movement of energy globally at a very low price in various tankers, oil tankers and pipelines, etc. These are the arteries and veins of any modern economy. We depend wholly on this. And so if you look at the energy use and the development of modern economies, it started, of course, in the 1850s or so. And energy use is the foundation of almost everything we do in modern life. And the research in that led to the laws of, as we know now, laws of thermodynamics in the 1850s, electromagnetism thereafter, and many other laws of science in the 19th and 20th centuries. And all of this development is based largely on fossil energy. 80% is fossil energy globally today. That, of course, has consequences. And as we now know, I don't have to explain in too much detail in this crowd, that the CO2 emissions is directly correlated with global warming and the temperatures going up because of the greenhouse gas effect. And while I'm showing only from 1880 to 2017, this has been the ups and downs of CO2 concentration in the atmosphere has been going on for hundreds of thousands of millions of years. But what we are seeing now is unprecedented because it is fossil energy that is being used, and it is doing so at a rate that is completely unprecedented in history. And as we know, because of the CO2 going up, the temperature does go up, sea level rises happen. And this is data from the past. The impact of this is not uniform across the world. Let me just show you what is going on in the Arctic. The Arctic air is warming at a rate much higher than the global average. The global average temperature rise is about 1.2 degrees from the pre-industrial level, but the air temperature has gone up by about 3 degrees in the Arctic, 3 or 4 degrees. The sea extent of the Arctic has gone down, and the sea ice extent, and the land ice in Antarctica and Greenland has gone down substantially. If you think that this is just an effect on the poles, you got to think again. These are the summer temperatures that are measured by NASA in the 1950s to now. And the summer temperatures, some summers are hotter, some are colder. They follow this very nice Gaussian distribution. And the hotters are the red color, and the cooler summers are the blue color. And the x-axis is the standard deviation. And what you see is the summer temperatures are going to the right, and you're reaching 5 times the standard deviation at probabilities 10 to 100 times than what used to be in the past, which is why you're getting heat waves. Every year, there are at least 1 or 2 heat waves, and we don't know where the next heat wave is going to happen. In 2019, there was a massive heat wave in India. In Rajasthan, the temperatures went up to 52 degrees Celsius. And last year, it was in 2020, it was in Siberia, where the temperatures went up to about 40 degrees, 35 to 40 degrees, which is unprecedented in Siberia. If you ask the question, where is it going to happen in 2021? We don't know the answer. But it is clear, and I apologize for using Fahrenheit scale out here, but 120 Fahrenheit is 50 degrees Celsius. The all-time high record temperatures are happening everywhere in the last few years. And this is only going to come to a neighborhood close to you. This is happening everywhere. If you ask the question, where does the CO2 come from and where does it go? What are the sources and sinks of CO2? We often think of the Amazon forest and the sub-Saharan African forests as the sink of CO2. It is indeed so. In fact, these are simulations from NASA. And you can see that in November, December, and winter in the north, you have more CO2 emissions because we need heating. We burn natural gas, and we need heating, and that's why the CO2. But the CO2 gets concentrated because of the jet stream in the North Pole, and it doesn't distribute evenly across the Earth. This is simulation. Here's the measurement using the Orbiting Carbon Observatory 2 and this OCO3, the 2 satellites that the NASA satellites that are measuring CO2 measurement. It's very poor coverage. They cover 0.7% of the Earth's surface once every month. That's the state of the art right now. And from those measurements, we are finding that while we thought that the forests in Amazon and the forests in sub-Saharan Africa are sinks of CO2, they're turning out, because of global warming, because of deforestation and others, they're turning out to be sources of CO2 almost as big or perhaps bigger than China. And this is very scary because we may be at a tipping point where it could be irreversible because now we have a positive feedback into the system. Just last week, a few of us, a couple of people from NASA, one from Berkeley and myself, we wrote an op-ed in New York Times. And can we predict these catastrophes, climate-induced extreme weather events, not 10 days or 5 days in advance, which is the current state of the art, but a month or 2 months in advance? And the answer is we are falling in the trap between weather prediction and climate prediction. But nature has no boundaries because now we know that the climate is influencing weather. And yet we have not quite developed the technology and the science and deeper understanding of how to do that. So we have a lot of work to do. If I move ahead, so let me interrupt this with a quiz for everyone. I'm going to throw some numbers, and I'd like you to guess what the unit is and what it means. So the first number is 1. I'll give you an answer. This is a quiz, there's no grading in it. The first number is 1 degree Celsius. This is the global average temperature rise since the pre-industrial level. It's about 1.2, but I rounded it off as 1. The second number is 2. And this is 2 degrees Celsius. This is the Paris Agreement that many countries got together, including India, and Prime Minister Modi was one of the leaders in that. And so was President Obama and President Xi and many others. This is 2 degrees Celsius because we know if the weather extremes at 1 degree are so bad, the 2 degrees can be terrible. And we really cannot predict what the 2-degree weather extremes are going to be, the heat waves, but we know that they're going to be worse than what it is for 1 degree. The third number is 800. This is not 800 degrees Celsius. This is 800 gigatons of CO2. If we are to keep the global average temperature rise below 2 degrees Celsius, we have a budget left of 800 gigatons of CO2 left in our budget, global budget. The fourth number is 40. 40 is roughly the rate of emission globally of 40 gigatons per year. Just to give you a reference point of what does a 1 gigaton mean, if you add up the weight of all 8 billion people on this earth, if you add up the weight and you ask the question, how many gigatons is that? It's about 0.6 gigatons. And we are emitting 40 gigatons of CO2 per year. The last number is simple. If you take the ratio, we got 20 years left. And if you don't reduce the CO2 emission rate, we're going to cross the 800 gigaton. We're going to cross 2 degrees Celsius. Where do the emissions come from? It is a variety of sources. Electricity production is about only 25%. Agricultural, forestry, land use, from food generation and fruit production is about roughly the same. Transportation is 14%. Industry, cement, steel, petrochemicals, that's 21%. And so it is not a single industry per se, but it is almost the whole economy that we're talking about. The world has never done this before, but if you are to keep the 2 degrees Celsius, this is what needs to change. I won't spend too much time on this except to say, this is one of the reports from the national academies, or what is the pathway we have to take? This is business as usual of CO2 emissions per year. The orange line is below 2 degrees, and the difference is what we call mitigation. We have to reduce emissions this is the magnitude of the emissions, but that's not enough. And I want to highlight that we need to get to net zero emissions, and the net zero can only be done by what is now being called negative emissions. We have to suck out CO2 from the atmosphere, which is at 400 parts per million. And those of you who know the laws of thermodynamics will be, it's obvious. If you're trying to separate out a dilute gas from a mixture, it takes a lot of energy to do that. And I'll come to that in a minute. But that's the challenge we have. So Steve Chu and I wrote a paper in 2012 while we were both in the Department of Energy. And this turns out, we thought Nature came and asked us, can you write a paper? And we said, okay, we'll do it. This has become very popular because it is the second highest citation of Steve Chu, slightly lower than the one that he did for optical trapping of dielectric particles, for which Art Ashkin got the Nobel Prize later on. And it turns out to be my highest rated paper. And we were not sure whether this will be read or not, but somehow it has been picked up by a lot of people. But one of the things we noted is a very famous saying by the former oil minister who passed away last week of Saudi Arabia. The Stone Age came to an end not for the lack of stones, and the oil age will end, but not for the lack of oil. The amount of hydrocarbons that we have in the ground is roughly the same in terms of the number of moles of oxygen we have in the atmosphere, because that's where the oxygen really came from, is the photosynthetic process. So we have to find better solution, just like we got out of the Stone Age, and we have to find better solutions for a sustainable energy future. And in this paper, we laid out some of the options. A more recent book is by Bill Gates that it's just come out, February 16th, it came out. I actually interviewed him last week at Stanford, and he actually laid out what the issues are in some level of depth, but there's of course much more deeper issues in that in terms of science and engineering, which I will go into right now. So what have been the energy breakthroughs and what is needed to really turn this whole global economy around? A lot of people think that unconventional oil, this is fracking, hydraulic fracturing and horizontal drilling has produced shale gas and made it really cheap. At least in the United States, it has displaced coal and reduced emissions by a factor of 2, as long as you don't have methane emissions. And if natural gas could be exported elsewhere, maybe they could get off coal. But nevertheless, this is not the real solution, not a permanent solution. The best thing that has happened, which was unforeseen even 10 years ago, was the price reduction of renewables. Solar and wind electricity generation have become the cheapest way to produce electricity. The yellow circles are solar in this case. The blue circles are wind, utility scale wind. And the horizontal line, which we thought was going to be the cheapest way to produce electricity, is from natural gas in the United States, which is really dirt cheap. So this is a trend, which is an amazing trend, which 10 years ago, we had never quite predicted, although we thought that this is possible. Maybe by 2030, but it turns out it's possible, but it became so in 2017 or 2018. The third one is the cost of batteries. This is lithium-ion batteries, which just got the Nobel Prize in chemistry. And today, the price of battery is about, for automobiles, the battery pack, is about $125 per kilowatt hour. In the next few years, we expect the battery pack price to come down to about $100 a kilowatt hour. And that number is very important because at $100 a kilowatt hour of battery pack, the range and cost of an electric vehicle becomes comparable to that of a gasoline with much lower maintenance that you would have. And so it becomes an economic issue then. And the idea of reducing the battery cost is all because of science and engineering, is because of the materials that are used to increase the energy density of lithium-ion batteries. So this is all about materials innovation and manufacturing that has gone into the battery pack. These three are amazing things that have happened, especially the renewables and the battery electric vehicles. But if you think that that is enough, that's far from it. Question is, what else do we need? There's a whole list of things, and I'll go a little bit into it, but let me give you an idea about it. Multi-day grid-scale storage. Small modular nuclear plants at half the cost of what it is done today in terms of construction cost. Refrigerants have a global warming potential about 2,000 times that of CO2. And as you increase refrigerator and air conditioner use, any leakage from that can have anywhere from 10 to 40% of the global warming of CO2 if you have these refrigerants go up in the atmosphere. Buildings are huge energy consumers. Many a times they're not designed to have energy efficiency. Probably one of the most important things is the industrial side of it. Steel and cement and petrochemical use a huge amount of energy and produce a lot of emissions. Can they be decarbonized? Either we use coal to make steel or we use gas for heating. And the question is, can we do it in a different way? Because the emissions are very, very significant. And finally, not often recognized as much, but 24% of the emissions come from food, a lot of it from food wastage, but inherently in how we grow food. And then there's the gigaton scale carbon management of removing CO2 from the atmosphere, putting it in the ground, and recarbonizing the soil, which takes into the agricultural side. So let me just step back a little bit and ask the question, what was the most important innovation of the 20th century? And a lot of people would think, oh, it's the computer chip or transistor or nuclear energy and all of that. It turns out, and there was a lot of study done at the turn of the century, there is none of those. What was thought of to be the most important innovation is the Haber-Bosch process of breaking the triple bond of nitrogen, combining it with hydrogen to form ammonia. The original catalyst that we use for uranium, this is 1908, before the before the nuclear age, and you needed high pressure, and that's where high pressure chemistry and chemical engineering really started. There were many Nobel Prizes given out of this, not just for Haber and Bosch, but even thereafter. And this is so important because none of us would be around if it was not for the nitrogen fixation that happened that's led to the food, and all that nitrogen fix are in our bodies right now. If you ask the question, what is the most important innovation in the 21st century? And there are several of them, but one of them has to be if you can take atmospheric CO2, combine it with greenhouse gas-free hydrogen, and make liquid hydrocarbons or fuel at $2 a gallon. And we don't know how to do that because we don't know how to capture CO2 from the atmosphere at a low enough cost or produce greenhouse gas-free hydrogen at a low enough cost. So let me say a little bit about some of the innovations that are needed that require science and engineering. The grid was never designed for wind and solar. I know there's a huge amount of wind and solar going into the grid now. It's still a small percentage, but the direction is very clear. There'll be hundreds of gigawatt being installed onto the grid worldwide, and the grid was never designed for it. So naturally, if you want to look at the fluctuations, compensate for the fluctuations of solar and wind, you need storage. And more the penetration of solar and wind, today we are at about 20%, 25% or so in many parts of the world, and you need a few hours of storage. As you go to 80% penetration, which a lot of people think is possible, you'll need 100 hours or hundreds of hours of storage at a time. And if you want to make it economical, and this is where the economic constraints come in, the cost of storage has to come down. And the cost has to be 1/10 that of lithium-ion batteries. This is where lithium-ion batteries today. This is the lowest limit of lithium-ion battery. This is where pumped hydro and some of the compressed air storage, and this is where we need to be. And we don't have any solutions yet for this. We have at Stanford, we have Steve Chu, and also have another Nobel laureate, Bob Laughlin, who are both working on this. They are looking at thermal, using heat, taking electricity, using joule heating to heat up something, and then use that high temperature heat to produce electricity, because that turns out to be the cheapest way to do so, even though the round trip efficiency is very low. Because in heating, every atom is used in the material you use for storage of the energy. Whereas in batteries, you have a lot of parasitic materials that you have to pay for. Hydrogen is going to be a very important commodity. Today, it is expensive. You produce hydrogen mostly from natural gas and sometimes coal, and there's a lot of CO2 emissions, and it's about $1 a kilogram, and we cannot get it down further, whereas the target really is about 50 cents a kilogram or so. And if you capture the CO2, the cost obviously goes up. A lot of people are excited about electrolysis. Today, you can take carbon-free electricity, you can make hydrogen, you can do this experiment in a lab, but if you really want to do this at scale, today it's about 3 to 5 times that of what you can get from natural gas, and potentially you can get it about $1 to $2 a kilogram, but not lower. There's also, you take natural gas and pyrolyze it, and the question is, can we get it down below $1 a kilogram? And this is going to be a very important topic, and we really don't have a solution for this. It is very important that we have some level of carbon capture. And the carbon capture are done by sorbents. Typically, we have used amines in the past, and we concentrate the CO2, and then we release it in a concentrated form and separate out the CO2 from a mixture. Whether the mixture is an exhaust of a coal-fired power plant, or a natural gas power plant, or the atmosphere. And as you make it more and more dilute, the laws of thermodynamics tells us you need more energy to overcome the entropy of mixing. So today, in a coal-fired power plant, the cost of carbon capture at about 15% CO2 is about $60 to $70 a ton. For gas-fired, it's about $90 a ton. And from direct air, it's about $500 to $600 a ton. And that is, all three of them are cost prohibitive. The question is, can we bring it down by a factor of 10 or so? And this is a very hard problem, but of course you cannot violate the laws of thermodynamics. So how far are we from the laws of thermodynamics? It is fairly easy to calculate the minimum work that is needed, minimum energy that is needed for the entropy of mixing. And for atmospheric CO2, that's about 125 kilowatt hours per ton of CO2 that you remove. Today's techniques are a factor of 20 higher. And at that factor of 20, it is going to be impossible, because if I were to remove 1 gigaton of CO2 per year, I would use up all the carbon-free electricity produced in the United States, including nuclear, wind, solar, and hydro. It's about 6 exajoules. So the energy cost, and this is really an energy problem to separate out gases from a mixture, especially if you want to do negative emissions, it's a factor of 20 above. If we can get it to a factor of 2 or 3, you cannot get it to the thermodynamic limit because the kinetics is 0 then. So you got to get it to about a factor of 4 or 5, and then you have a chance of minimizing the cost. And that's where the research needs to go. I won't spend too much time on the sorbents, but some beautiful work coming out on cooperative binding of CO2 with what are called metal organic frameworks, which are extremely interesting materials, but they also need to do this at scale. Let me end my talk with what we grow and what we eat. This is a fascinating area, and I'm getting more and more fascinated about this because I like food. But the problem is the following. The CO2 emissions for every 100 grams of proteins that we eat has a huge impact on what the source of the protein is. If you're eating dairy beef or beef, you are at this level, is the highest CO2 emission. For 100 grams of protein from beef, we emit 25 kilograms of CO2, which is a huge number. If it's lamb, it is slightly lower, but still very high. And as you go down to farmed fish or tofu or beans or peas and nuts, is negative emissions. And so what we eat makes a massive impact on the carbon emissions, because 24% comes from the food and agricultural side. Just to give you where the food trends are, this is the meat production per region: Asia, Europe, North America, South America, etc. Others are stable, but Asia is going up dramatically. Where is that coming from? It's not India. India is flat. Luckily, many of us eat vegetarian diets. It's flat. China is going up. Brazil is going up. And as people become more and more wealthy, they have more income level, the meat consumption seems to go up. And we have to figure out, because if you don't solve the meat problem and the dairy problem, we have a real problem in our hands, because we will not be able to curb the emissions down to keep the global average temperature rise of 2 degrees. So what kind of innovations can you have? I'll give you one example, which has come out of Stanford, and that is the science and engineering of food. This is fascinating. It came out from the same person, Pat Brown, who developed microarrays of DNA, and he has now started this company called Impossible, where all the meat is from plants. Now, this is not the first time this has happened. A lot of people, there are lots of vegetable burgers and all of that. But what is interesting out here, and the science behind it, is the fact that they were artificially able to grow the molecule heme, which is the hemoglobin, which is where the oxygen binds. And that's the iron that gives you the taste of blood in meat. And they were able to take the gene sequence that gives you, and look at the pathway that is used to produce the heme. And this is actually produced in soy, in the roots of soy. They were able to replicate that in yeast production. And now this is the heme produced in yeast that goes into vegetables and so a little bit of coconut oil and other oil. And if you taste the meat, it tastes almost the same as meat. This is the kind of innovation we'll need. There's a lot of innovation going on in the food industry. And if this is the approach to use plant-based meat to satisfy the meat craving that people have, maybe this is a way to address, and this will require fundamental science and engineering to get it done. Let me end my talk by saying that when I talk about the defining challenge, they call it a defining challenge because it's not one sector. It's not just the electricity or the transportation. It is electricity, it is transportation, it's steel, it's cement, it is food, agriculture, it is all of the above. And I'll leave you with this parting thought that whatever 10 billion people consume today, the way we approach today, will produce gigaton scale CO2 emissions, whether it's electricity for heating or cooling, transportation, food, textiles. Textiles are projected to have 10% of the global emissions because we all have to wear clothes. Water, pumping water, steel, cement, information technology, if it's not checked, that can take up about 20% of the electricity the way we all use information. And all of them need energy. And the new solutions will require, we need new solutions. There's no question about it, because we cannot look back at the 20th century for solution. And new breakthroughs will only happen through science and engineering. Let me stop there. And I thank you for your attention. Over to you, Professor Ghosh.
Thank you, Professor Majumdar, for a wonderful, very enlightening talk about the challenges, the immediate challenges that we face. I mean, the challenges are huge, so the technologies, the science that we need to do, but it's also scary. The prospects, if we don't do something, they're really scary. So maybe that's the wake-up call that, well, we've been getting wake-up calls, but I think we are not really waking up to what should be done immediately. I'm glad to know that there are lots of efforts. And may I now invite questions from the listeners, from the audience. So please unmute yourself and we could take a few questions to Professor Majumdar. So, or you could put it in the chat box here.
Ravi,
Yeah.
Vivek is raised his hand.
Okay, so please.
Vivek. Okay, can you hear me, please?
Yes, yes.
Yeah, okay.
Yes.
My question relates to the graph that you showed where the lithium ion battery has, there might be some improvements, but it will come to the limit soon. So what is there on the horizon if you want to do better than lithium ion batteries?
Well, as you know, lithium ion battery, the innovations that are happening are certainly on the cathode side, on the anode side. The anode, the big one is pure lithium metal with a solid state separator. And the anode side is, these are ceramics, oxides. But if it could be done with lithium sulfur in a rechargeable way, that would be a quantum jump in energy density and thereby the cost. Sulfur, the oil and gas companies will pay you to take the sulfur away because there's a lot of sulfur in sour gas. There's also an approach which is very hard to make it rechargeable, but the attempts at it is take iron and sulfur. And that's a redox pair that could be used as a chemical storage, electrochemical storage. But again, these things, to make it rechargeable over many times is difficult. There's manganese and hydrogen. There are many combinations of these redox pairs that you use. But the fascinating part, which with Steve Chu and both Steve Chu and Bob Laughlin have gotten involved, and there are several others, they're not the only ones, is to take the simple idea of taking electricity and using joule heating to heat up something to high temperature, and then using the thermodynamic potential of high to low temperature in the exergy to produce work through a turbine. And the reason that turns out to be cheaper at scale, at large scale, is because as opposed to electrochemical system, in a heat-based system, every atom is used. Because all the modes of vibrations are elevated, every atom is used for the storage, whereas that is not true in electrochemical systems, and thereby the cost goes down. So I think we have to think in a much more innovative way and question some, using the laws of physics, question some of the traditional approaches and see if there are new approaches available.
Thank you.
Thank you. Do we have more questions from the participants here? Anyone else? Otherwise, I have some questions.
Ravi?
Yeah.
Jitu here.
Yeah, please go ahead, Jitu.
Yeah, maybe I can ask a question to Arun.
Yeah, do. Please go
Hi,
ahead.
Arun.
Hi.
Yeah. Fabulous talk. I must say that was a real, sort of a breathtaking kind of perspective of where we are and where we are headed. So obviously the choice is that we, don't have the luxury of doing nothing, right? I mean, that's basically what you're saying. And I was just wondering now, in the context of the last part, which in some sense concerns every single human being, which is food, and of course water and textiles, as you indicated. I mean, in these areas, how are we going to think about programs that could be creating a reduced carbon footprint, given what we already have on the plate? I mean, I just wanted you to take some sort of a bird's eye view and give us some perspective on that.
Yeah, so it's a great question. Good to see you, Jitu, after many years. For those of you who don't know, we were classmates in IIT Bombay.
And good to see you, Arun. Yeah. We didn't call you Arun then, though.
That's right. So this could be answered in many different ways. There are personal choices you have to make. There are industrial issues, and there's government policy. If people go off meat in many parts of the world, and I have to say in the United States, if they go off meat for 1 day a week, it is a big difference in CO2 emissions. Now, will people do that or not? I don't know. These are personal choices, and it depends on the next generation of people making those choices. Now, if you make things like Impossible and others through innovations that make it taste like meat and you don't find a difference, that's even better. Because then you're not consciously making a choice or making sacrifices. But you got to, at some point we have to make these choices and figure out, where do we want to, how do we want to reduce our own CO2 footprint? There's also the industrial side, and that is we have to make things cheaper and better. And so if your electric vehicle can be cheaper and better than a gasoline vehicle, and you have enough charging widely available, why would anyone use a gasoline car? Right? Because you got to change the oil and all of that. Here, you don't have to do that. So I think there are some other industrial, and this requires not just innovations in science and engineering in the next generation battery, but also products that have to be made by car companies. And you just heard General Motors are not going to make any gasoline cars after 2035. They made a decision. Volkswagen did the same. They have realized that that's the future, and they're making the bet on that. And the oil and gas companies are now saying we're not any oil and gas companies, we're energy companies. Shell, Royal Dutch Shell, now are acquiring charging companies, charging station companies, electric utilities, etc. They're broadening themselves. So these are choices people are making purely from business economic reasons as the right choices. And that will, I think, make a big difference. And these are all triggered by government, many times by government policy. And policy matters. Leadership really matters in this case. And that is that if you want to manage carbon, you have to have either a direct or an indirect price of carbon. Otherwise, why would anyone take CO2 out of the atmosphere and do something with it? You got to give a price signal. And the price signal has to be predictable so that the businesses can plan out their capital outlay for the next decade so that they can actually approach it in the right way, in a business friendly way. If the policies from the government keep oscillating, as we have seen in the United States, then the business cannot really adjust to it, cannot plan out. So it's a really combination from personal to business to policy, but there's no question you need breakthroughs using science and engineering to make it much, much easier and to make it actually happen. Without that, policy alone is not going to get us there. Technology alone is not going to get us there, but the combination and reinforcement and alignment is the critical thing in the future. It's a long answer to a short question.
Ravi,
There's a question here
question
from
in chat box.
yeah,
from
and from Arnab Bhattacharya, who works on semiconductors and solutions like that. So he says, even for solutions like raising water to a height to store potential energy, isn't effectively every atom used? So is there a comparison of this efficiency of this versus the heating approach? And is the heating mostly aiming for latent heat of melting?
It's a great question. The cheapest way today to store electricity is pumped hydro. You're absolutely right. And there are many hydroelectric dams that are producing electricity. There are many in India, and there are many in the United States around the world. But most of them are not retrofitted to do pumped hydro. And to do pumped hydro, you not only need a tank on top, but you need a pool of water at the bottom as well, so you can pump water up and you can use that for storage. And the good thing about hydroelectric, when you actually already have a hydroelectric plant, the grid connection is already there, except it's one way. And if you can make it pumped hydro, you can make it both ways, and that is the cheapest way to store electricity. So I know that in last April, you had this in the candlelight vigil in India, where all the lights had been turned off because of COVID. And the only reason the grid in India did not collapse is because of hydro in the north that was used. And so hydro turns out to be one of the most important things. So Arnab, you're absolutely right. And for the latent heat part, yes, the latent heat is obviously, that's where a lot of enthalpy can be stored. And if you need less material, which means less cost. You're absolutely right.
Yeah, Professor Majumdar, would you like to stop the share because they want to see you in a bigger frame? Right now, you're being seen as a small.
Oh, I see. I think I've stopped my sharing.
There's somebody else sharing, actually. I don't know how it happened. But,
this is not my sharing.
We still see the Zoom post attendee.
Oh, really?
Yeah.
I don't think that's mine.
Okay. So,
there's some other comment.
Okay, but let's go ahead with the question anyway. He says, rather than convert, there's one question from Professor Vivek Polshettiwal, who also works on energy-related issues at TIFR. He says, in addition to capture and storage of CO2, shall we not invest in developing technology to convert CO2 to fuel? So it's a cyclic economy, he says.
And yes, I think I mentioned that in my talk. That would be, if he could do that in a way that is cost effective. Again, you have to then compete with oil. So the only so let me back up and say this, that the only thing that is at scale comparable to the carbon emissions from fossil fuel is, of course, fossil fuel. So if you could turn that around and make fuel from CO2, that would be the right way to do it because it's at scale. But to turn CO2 into fuel, you need hydrogen. And the hydrogen better come from sources that do not have greenhouse gas emissions. And that hydrogen has to be 50 cents to $1 a kilogram. That is the big challenge. And so there is no free lunch out here. And we have to crack the nut of how to produce hydrogen at scale at less than $1 a kilogram.
I
And we don't know
dare
how
say-
to do that.
Yeah, in a way, I think we have exhausted all the freedom that Mother Earth gave us, and now we really have to scramble to find solutions. Now, there's an interesting question from a computer scientist here, Akradev Chattopadhyay. He says, let's compare two scenarios: 1 day off meat a week. And the second one is people giving up SUVs and buying smaller cars. And yet another one, he says, is changing the American way of life. That is increasing sprawl and living in condo more huddled up. So can you compare all these alternatives?
All of the above. All of the above. I don't think it is one or the other. I think we fall in the trap of what I call tyranny of or. Because it's either this or that. We have to have all hands on deck right now. And it is, yes, if more than 1 day a week, that'd be great. I grew up eating red meat. Okay, I've given up. And the only thing I can do is maybe eat fish once in a while. And so you got to make some choices. And if I'm going to preach this, I better make the choice myself. I'm mostly vegetarian nowadays. People giving up SUVs, absolutely. Public transportation. If you can make public transportation viable, that would be the right way to do it, not just going small cars. And changing the American way of life, including small, I completely agree. That is the right way to do it also. So it's all of the above. By the way, just on the...
Sorry, Ravi, I'm taking the liberty of jumping in. Yeah. No, I agree, all of the above. That's the ideal case. But, you spoke about one, I'm also very fond of meat, and I have to, daily confront this and somehow rationalize my still continuing with meat. So I was just asking, what are, if you have some idea of the comparisons, like 1 day off meat, or buying more economical cars, or living in condos rather than, are they sort of comparable in cost, or do you have some of them giving you much, much bigger cost savings, yet not so much touted in the media or anywhere?
That's a great question. There is some equivalence. If you eat 1 kilogram of, let's say, goat meat, lamb. Now, I'm not saying everyone eats 1 kilogram at a time, but 1 kilogram is almost equivalent to driving your car for 100 miles.
Wow.
Okay, so you can make those comparisons. In fact, it's very important, if you are to do this, is to put some numbers out there. Because the numbers will tell you which are the majority of the homes. I can't tell you how important insulation is for homes, and because then you use your load is much lower for air conditioning or some other, but you do need ventilation. So energy efficiency of homes are one of the most important low-hanging fruits. But there are some market failures. Price of electricity for people who are wealthy doesn't matter, because you just pay off the electricity bill. So there are other factors that are involved that are non-technical, but they matter at a time. By the way, I just want to make a note on the hydrogen. It's not that we don't know. If you can figure out a geologic source of iron 2+, okay, which is there in rocks, etc. Iron 2+ going to iron 3+ will split water and produce hydrogen. Okay, that is a reducing agent. And so there's some thinking going on, is that can we use geology at scale to go from iron 2+ to fine iron 2+ and go to iron 3+, because that is that redox reaction can do it. In fact, there are hydrogen reserves that have been found, presumably because of presence of iron 2+ and rainwater going down, and then enough of the geologic heat to be able to do this. So I think one has to think in different directions to be able to solve the hydrogen problem.
Okay, there's a question, I believe it's Professor Alakre, our ex-colleague. He's from YouTube. He asks, many say nuclear is the only viable renewable considering the myriad issues with solar and wind. How true is that? Would you say that nuclear is the only alternative?
Nuclear certainly should be on the table. The problem with nuclear is really the cost. And it is not the science is well known, the engineering is known, but in the United States, I can tell you, it's a construction cost of nuclear is too high because we haven't built a nuclear plant since 1980s. Okay, so we haven't built, so the cost has gone up because unless you build more, you make mistakes, and thereby those mistakes are costly. And so, whereas South Korea builds nuclear plants at half the cost of the United States, and that is the right way to do it. So, I think nuclear fission certainly should be part of it. Whether it is uranium-based fission or thorium-based fission, we can debate that. But the fission-based power generation has to be on the table, and it has to be cost-effective.
But it could also be the ITER kind of, the thermonuclear
fusion. Well, believe me, this is something that Department of Energy was deeply involved for a long time, and still involved.
Yeah.
The problem with fusion, as many of you may know, is still a science problem. We still don't understand completely whether it is magnetic confinement or inertial confinement. What are the instabilities, the plasma instabilities that are there? And unless we do that, we will not be able to compress in the right way.
Yeah.
And so we can't, while we need to pursue the science and really understand what's going on, we can't rely on it as a viable option yet. Only when we understand the science, then we can control fusion and thereby get net gain greater than 1 and produce energy. We're not there. We're far from it right now. So I know a lot of people are optimistic about fusion. I'm all optimistic. I'm on the advisory board of a fusion company in UK in Oxford.
Wow.
And I want them to be successful. But there's a road ahead.
So I know it's getting late for you, but the questions don't stop coming. But I'm glad that there's so many questions.
Sure.
Your talk was extremely, provocative in the sense that we have to find solutions quickly. So there's one question here: is the fuel cell technology too expensive?
Fuel cell is an energy conversion technology. It's going from fuel to electricity, right? It is one of the options. It is not it's like an engine. You can run the fuel in a internal combustion engine and put a generator and generate electricity. So fuel cell has to compete with that. It's not an end in itself, it's one of the solution aspects of it. But it is not as cheap, frankly, as internal combustion engine. Those are really dirt cheap now. But fuel cell is important because the overall system efficiency can be high, roughly 50% or maybe a little bit higher than that, which is hard to get for internal combustion engines unless you're doing gas turbines. The natural gas combined cycle turbines are 60+% efficient. It's very hard to compete with that.
Well, I'd like to ask if Professor Ramakrishnan, Professor Ghosh, do you have any questions before we take a last couple of questions from?
Yeah, I just have one query. Will the solar wipe out the need for nuclear energy? The rate at which the prices are going down, and what's your opinion?
Well, I think you can. Solar costs are coming down, but the grid was never designed for solar. We have to realize it has to be integrated into a system, and when the sun goes down, you don't produce any electricity, so you got to store it. So I think it's very important when we are doing solar at scale. Let's say you have 60-70% penetration of solar plus wind. Let's say you have that. Then the cost of integration needs to be included. And that's why I emphasize on storage technology at cost, because that is the missing piece right now on supporting solar and storage. You can manage the grid up and down by managing load. You can do load shedding, and we know all of those technologies, and you can do it in a smart way. Let's see, get that. But at some point, the sun goes down and the wind may not be there. So you need some level of storage, which is why pumped hydro and all the other techniques become so important. And if you do that, yes, you could have solar penetration, but I do think you need base load carbon-free electricity, which is the only way to do that is either hydro or nuclear. And when the population density is high, you need land use is important, and nuclear seems to be the only way to have high density source for electricity.
Thank you. It's gratifying to know that.
Okay, it's good for us because we are Department of Atomic Energy. So, and the other thing with nuclear is that it raises lots of, doubts and suspicions in the minds of people because of the accidents that unfortunately have happened over the decades. Even though the technology is very well known, we have to face a lot of societal opposition, which I think in India, there are lots of NGOs which are against nuclear power, and they raise the flag and they stop the construction of the plants. So it's a huge battle of, you have to fight the battle on that front too. But I have a couple of last things. Some time ago, I read somewhere that, we have gone so far down the road now that even if we wish to convert to safe energy right now, and the amount of expenditure, the amount of emissions that will be caused by the conversion to safe methods itself will overwhelm us. Do you agree?
What do you mean by safe method?
Meaning that we want to get to lower CO2 emissions, and we improve our technologies and all that. But the amount of effort that we make to get to that point will itself consume so much of energy that, at the end, what have we achieved?
Yeah, so I mean, in all of these things, when you make a solar panel, for example, there's energy use for that. But there's a lot of analysis that goes into the life cycle energy use. And, for example, solar, it makes for its, you compensates for the energy used in a few years. It exceeds that. I mean, let's talk about nuclear. Nuclear plant.
But the emissions, I'm sorry to interrupt, but the emissions that are caused for this energy to be used for making solar panels and stuff like that, that itself defeat the purpose of changeover.
That is not true. If you look at solar over its lifetime, it's not true. These are, there's a scope 1 emission, there's scope 2 emission, and scope 3 emissions.
Okay.
It's easy to reduce scope 1 and scope 2 emission because, you can go from like Google and Apple and Microsoft are all doing that because they can afford to buy renewable power, et cetera, right? The scope 3 emissions is the most difficult. And that's the majority of the emissions because it's along a supply chain. So if someone's scope 3 emissions is someone else's scope 1 and scope 2 emissions. So I think it is very important to go across the economy holistically and try to reduce CO2 emissions so that even when you're trying to make, let's say you try to build a nuclear plant to produce carbon-free electricity, the cement and the steel that you use in the rebar, concrete and all will have CO2 emissions embedded. But if you can decarbonize those sources, which is why I was insisting on, you've got to decarbonize cement and steel. Now, you may think, oh, those are old industries and all, but that's where the problem is. If you really want to solve it, that's where. So if you want to build a nuclear plant for green cement and green steel, that would be the right way to do it, but you got to decarbonize those too. You can't just build a nuclear plant. So I think one has to take a economy-wide holistic approach. And I must say, please read Bill Gates's book, and he's absolutely right. The humanity has never done this before. This is not just World War II or anything. This is even beyond that because it'll touch every human being on this earth because those weather extremes will affect people, whether it's floods or low-lying areas of the Ganges Delta or the glaciers bursting open because of hitting a local tipping point. It's going to come to your neighborhood at some point. So I think one has to address that holistically.
Well, in India, we've already had it. For example, it has come way inside now. We've had the highest temperatures over the last few years, and we have had storms that were totally, unprecedented. So I think it's notwithstanding what the political leadership in the US said till recently, that there's no global warming. But I think it's a reality.
Thankfully, we have a different administration.
Well, so a couple of things before we close is that, it's interesting that you point out that Steve Chu and Bob McLaughlin are the two people spearheading this energy efforts in the US. And it's interesting that Steve Chu won the Nobel Prize for laser cooling, and Bob Laughlin, if I'm not wrong, won it he's a theorist who won for the fractional quantum Hall effect. So
That's
something
right.
that our director said at the beginning, that basic scientists are also deeply, deeply engaged, because it's a matter of survival now. We cannot ignore these problems anymore and keep doing our own, blue sky research. Probably we have to have some middle way, and that's in tune with the times, I guess. And also we spoke of food a lot, and it's approaching lunchtime here. And of course, it's well past your dinner time. So on that note, we thank you very, very much for a wonderful, engaging, provocative, and very, very challenging talk. And I think the next time you're in Mumbai, certainly we'll have you over at the auditorium, in the Homibhav auditorium here, and we'll listen to you on how we take this forward.
Yeah, so, and also host you a vegetarian lunch.
Vegetarian lunch. That's two vegetarians here. And
it'll be my honor. Thank you so much for the honor of inviting me.
The world has to be vegetarian now, though the meat eaters might find it very difficult to convert themselves. So we need that happening. So Dipan, any other?
Fish eaters are not doing that much of damage.
That is true.
So we draw the line there.
Should be a fish eater.
Yes. So thanks very much. It's been a great experience. And Professor Majumdar, we can't thank you enough for this wonderful Science Day lecture. So
thank you.
My pleasure. Thank you so much. Thank you. It's been my honor.
So we will place this lecture on YouTube and also send you a link that you share it with other people. And I'm telling everyone, there was a little bit of a glitch in the beginning, but I think that we have sorted out. And so the full recording would be there on the YouTube. Apologies for the initial glitches. So thanks everyone. And
thank you.
Good day. And good night to you.
Bye.
Good night.
Good night.
Good night. Yeah.
Good night, Arun. Yeah. Bye.
Good night. Thank you.
Ravi, shall I close?
Yeah. Dipan, I'll call you.